Hello, in this third module of the discussion and analysis of variance, we're going to be looking at two-factor ANOVA with interaction. And you can pause this tape for a little bit and read this story right here. But here's the quick summary of this. Here's a data set. So we're interested in looking to see if the average percentage of water removed from paper specimens differs across different levels of temperature as the specimens go through a certain device. So the temperature is set at either 100 or 120 or 140 degrees Fahrenheit. If it is set at 100 degrees Fahrenheit, these are the samples that we obtain. At 120 degrees Fahrenheit, these are the samples. And 140, these are the samples. Equally, we're interested in learning to see if there are differences in the average water removed from the specimens at different times of passage through the device. So for example, when the device could be set such that the papers go through it over a period of just 10 seconds or 20 seconds or 30 seconds. So do we have a statistically significant difference in the average percentage of water removed across the three levels of exposure times? So this is a two-way ANOVA as you can see it. So on the one hand, we're going to be looking to see if there are differences across different temperature levels, as well if there are differences across different exposure times. Thirdly, however, we're also going to want to see if in fact there is an interaction between time and temperature in terms of the percentage of water removed. And that's why we have these in blocks. For example, these four observations here, 24, 21, 26, 25, are going to be the average percentage of water removed when the device is set at 100 degrees Fahrenheit and 10 seconds of exposure time. And this one here is going to be when the device is set at 140 degrees Fahrenheit and 30 seconds of exposure time, and so forth. So let's rock and roll. So first, we show our statements of hypothesis. Here I just simply show the null hypothesis. You would know how to describe or define your alternative hypothesis. So for example, for temperature, we want to the null hypothesis is that the average percentage of water removed is going to be the same across all three temperature levels, and this is going to be that the mean level of water removed is going to be the same across all three exposure times. And then for the interaction is going to be that there is no interaction between temperature and exposure time. In other words, there is no extra effects associated with the combination of these two main effects. You know, it's pretty much like drugs. You know, you're given a drug that is designed to cure high blood pressure and another one that's designed to cure headache. And the question is, will the two drugs, in addition to taking care of your blood pressure and headache respectively, is there an interaction effect in that when taken together there is an additional effect in your overall health, for better or for worse? So anyhow, so we're going to calculate the sum of squares treatments, and there are going to be two treatments, temperature and exposure time. As is the case in a one-way ANOVA, treatment sum of squares is going to be the difference between the mean for each particular level of treatment and the grand mean. And then we're going to square and multiply it by the number of observations. So if I go back here real quick, we're going to look at this mean of 39 and look at the difference between this 39 and the grand mean of 52.31, all right, squared. And then we're going to multiply by 12 because 12 is the number of observations under temperature level of 100 degrees. And we're going to do the same for 120 and 140. So 120 is going to be this mean of 51.92 minus the grand mean squared multiplied by 12. And for this guy here is going to be 66 minus 52.31 squared multiplied by 12. And that's precisely what you see right here. All right, that's what we did right here. And then you add them all up, and this is your sum of squares for temperature. And let's call that factor number 1 For exposure time, we do the same. So if I go back here, it's going to be the difference between this number, this mean for exposure time setting of 10 seconds, all right, this number minus the grand mean of 52.31 squared multiplied by 12, because again we have 12 observations in this yellow block, and we're going to do the same for this and for this going forward. That's what you see done right here for exposure time, and this gives us the sum of squares for the exposure time. Now though, for interaction, first of all we need to calculate the means for each block of interaction. For example, going right back here, for this block right here, 100 and 120, we take the average of these numbers. 120 and 10, we take the average of these. 140 and 20, we take the average of these, and so forth. So that's what you see right here, right? So I've shown you a couple of examples here for 100 degrees Fahrenheit and 10 seconds of exposure time. This is the mean based on these observations. So when we get all these means, now we can go ahead and calculate the sum of squares interaction, which as you see here takes the traditional form. So again, it's going to be the difference between each interaction mean and the grand mean squared multiplied by the number of observations in each set of group of interaction numbers, and it's going to be 4. So that's what's done here, all right? The interaction mean for 100 degrees and 10 seconds, all right, and that's minus the grand mean squared multiplied by 4 observations within that block. So we get this number, and in the same way we do that for all the other interactions shown. So now we add up all these numbers, and that's what you see here. This is called the interaction total, 12,680 and 80. So now to strictly identify the portion of overall effects due to interaction, we subtract from this 12,680 sum of squares for temperature, which is 4376.69 that we calculated earlier, in addition to sum of squares exposure time, which is 8,197 and change. So we take these away from this interaction total, and what's left is the portion of the overall effect associated with the interaction of time and temperature, 103.28. In step number 5, we wrap it up by calculating the sum of squares total. Again, sum of squares total is going to be each observation minus the grand mean squared. So going back to our data set, it's going to be each of these observations, for example 24 minus the grand mean of 52.31 squared. We do the same for each of these numbers. Tedious exercise, I'm sure you would agree. So I didn't show the work here, I just showed you the final answer because I actually did that on Excel. So this is our sum of squares total. How about sum of squares error? Well, it's easy. We do that by deduction. We take this sum of squares total and subtract from it all the sectional sum of squares. Sum of squares temperature, which is this, exposure time, which is this, and interaction, which is this. The residual, whatever is left, is going to be your sum of squares error. So that's a quick way to do it if you want to do this manually. This is the summary of it. So sum of squares temperature, sum of squares exposure time, sum of squares interaction, and sum of squares total. This minus this, this, and this will give you the difference of 129.25, which is our sum of squares error. Degrees of freedom for temperature is the number of levels minus 1, C minus 1. So I use C to denote columns. There are 3 levels, 3 columns actually for the temperature. And for exposure time, I use R for rows. Alright, so going back here, you see columns for temperature 1, 2, 3, and rows for exposure time 1, 2, 3. Alright, that's why I chose to use C and R to make it intuitive. Alright, and so each of them will have 2 degrees of freedom. For interaction, it's going to be the product of those 2, which is going to give us 4. Total degrees of freedom is always going to be n minus 1, the overall sample size of 36 minus 135. Therefore, the degrees of freedom for error is going to be 35 minus 4 minus 2 minus 2 would give you 27. So again, it's the difference. And as is typical, the mean square for this first treatment temperature is going to be the sum of squares divided by degrees of freedom to get this 2188.36. You do the same for exposure time, dividing the sum of squares by the corresponding degrees of freedom. And do that too for interaction, dividing the sum of squares of 103.28 by its degrees of freedom of 4 to get the mean square for interaction. And their F statistics is going to be the mean square value divided by, you guessed it, mean square error. Here, mean square error is 4.79, which is this sum of squares divided by 27. So by dividing each of these mean squares, temperature, exposure time, and interaction, we get their F statistics. So all we got to do is go to the F table and look up the critical value. The critical for interaction specifically, if I go here, again, the interaction is going to be, the degrees of freedom is going to be 4 in the numerator, and of course the denominator is error. It's 27. So 4 and 27. And that's how you get this 4 and 27. So based on this, we find the critical value to be 2.73. Let's do this. So this is the F table. So again, we're looking for 4 and 27. All right. So 4 at the top, 27, let's scroll down right here. That's critical value, that's going to be this guy right here, 2.73. And that's what you see right there. All right. And as you can see, the calculated F statistic of 5.39, which is this number right here, exceeds the critical value, causing us to reject the null hypothesis and concluding that there is sufficient evidence that temperature and time, exposure time interact. So in the same way, we find the critical value for temperature based on the degrees of freedom there. And we're going to be rejecting the null hypothesis for temperature as well, because the calculated F exceeds the critical value, and ditto for exposure time, whose calculated F exceeds the critical value. So we can do this quite so easily in Excel using ANOVA two-factor with replication. So let's do that real quickly. Here's our data set, and we're going to go to data and then data analysis, and then right here we want to go to two-factor with replication. Okay. For input range, you highlight these as I show right here. Right, making sure to place the labels of temperature levels and exposure times in the ways that I did at the beginning of each row for exposure time and on top of each column for temperature. Now, incidentally, on Excel we don't have any provision for labels, and that you wouldn't see any label right here, and that's why we have avoided the words temperature and exposure time. So all I highlighted are these values here. So rows per sample, well, rows per sample, let's see, 1, 2, 3, and 4. So 4 rows per sample. So we type in the number 4 right there. Let's leave this at the 5% level. If you want it to be 1%, go ahead and type in there and change that to 1. Click here for output, and then click here for, so the cursor can blink while you choose a spot right there somewhere on the spreadsheet for your output. Okay. So here we are. Let's raise the size a little bit to make them more legible. So this is it, ANOVA two-factor with replication, and Excel gives you the summary data for each level of temperature as well as each level of exposure time, as you can see right there on the side, right? So now, but more importantly, we want to go down here to the ANOVA table right there, and here we can format our data a little bit better. All right, go here and let's choose number and choose that one right there. All right, So we can see based on their p-values that all of these outcomes are statistically significant. But look at how Excel labels this. All right, we know what interaction is, but it says sample and columns. For column, well, let's go upstairs right here. We know that column has got to be temperature. So surely what it calls column, we can go ahead and help Excel out a little bit and just type temp right there. All right, and that tells us that sample is got to be exposure time. All right, exposure time. All right, for clarity. So within, of course, is error. All right, so now we're looking good. And based on this, I copy over right here on PowerPoint to make it real nice for you to quickly understand. So here are the sum of squares, the degrees of freedom, the mean squares, and the calculated F values. Here are the critical values. So you could either compare the calculated F value to the critical value, do that for each of these three outcomes, or you simply look at the p-values and compare the p-values to the level of significance that you choose. Now, as you can see from these results, you would be rejecting the null hypothesis for the two main effects of exposure time and temperature, as well as interaction. All right, and therefore you would proceed perhaps then to go ahead and do a Tukey pairwise comparisons to find out which of the levels of exposure time and which of the levels of temperature are statistically different one from another.